Okay, this is a continuing video looking over week two's patches. We left off with Metro. Now I'm opening up number 8, Env with line. A lot of times in computer music, what you're trying to do is control pitch and volume. This is kind of the classic note on, note off experience. And when you're doing that, you're trying to make ramps. So you're fading up a sound, holding it for a period of time, and then fading out that sound. This is an oscillator set to 440 hertz. It's producing that tone at a constant -1 to 1 amplitude. And then we alter its amplitude using the multiply tilde object by the output of this line tilde. And to begin with, line tilde is set to 0. I can then fade up to 1 over 100 milliseconds and fade down to 0 over 1 second or 1,000 milliseconds. If I want to graph how that looks, so you can see the output of line over here, I'll do that. So this bang triggers the graph and then waits 400 milliseconds and triggers the fade in. So you can see it looks like this. And then this will graph again and graph the fade out. So you can see a longer fade out there. I'm clipping here just in case things got too loud, and then multiplying by 0.05 to bring the volume down. So that's the basics of making a little envelope. Now what we would want is a way to control all of these messages in one go. And so delay can help us do that. Imagine if I were to connect not to this delay here, but instead here. So when I graph initially, it goes ahead and starts, then it waits 400 milliseconds, and then fades out. I may not fit all of that on one graph, but let's see what happens. Yeah, so I got my fade in, my wait, and my fade out. I could change the wait time. You can see fade in, doesn't wait very long at all, and fades out immediately. So that's the gist of how you would make a very simple envelope, amplitude envelope, with an attack time and a decay time. And if your sustain time is set longer, like 400 milliseconds, then you have a sustain time as well. Okay, let's look at MIDI values. So in computer music, we have to organize the pitch of a sound using frequency because our oscillators ask for frequency as a way of us telling it, how many cycles per second it needs to oscillate. But when you're looking at a MIDI keyboard or most standard Western instruments, the values we would think of as being related to frequency are really called pitches. And so, you have pitch C sharp, pitch D, D sharp E, F, F sharp G, G sharp A sharp B, and C. And so we can translate from that MIDI, what's called MIDI pitch space, into frequency by using the M to F object. And as you can see, while I click these messages, I've laid them out like a MIDI keyboard. So these would be the white keys of the keyboard. These would be the black keys of the keyboard. So C, D, E, F, G, A, B, C, and then these would be the black keys, C sharp, D sharp, F sharp, G sharp, A sharp. So notice when I click 60, it translates that MIDI value, and MIDI stands for musical instrument digital interface, and it translates that into frequency 261.6. And now if you go up an octave in MIDI values, which is up 12, up to 72, you can see that it doubles the frequency. So every octave is a doubling of the frequency. And so there is an equation that you can use to get this logarithmic relationship across these what are called half steps within an octave. And that equation is held within the M2F object. And I don't think, like, here's another thing. Every object in PD has a help file. If you right click and choose help, you can get to that object. And so M2F sits in this little help file that talks about how MIDI pitches are set to 440 hertz, and 69 is 440 hertz. That's the A above middle C. You can use decimals, so if you want to use microtones, that's entirely possible. And there are some other conversion objects in this same help patch. But with it laid out like this, I'll turn the volume on, and then I could play melodies. And so on. And so learning how to control a little system that uses MIDI note numbers instead of frequency might be a more intuitive way to make music if you're familiar with Western musical scales. So there are some cool things about what's called 12-tone equal temperament, and that is the tuning of those individual notes in the octave. It lets us play in lots of different keys. We can talk about this more in class if you want. But in actuality, those relationships are not perfectly in tune in a mathematical way. So this little patch lets you sort of test some of those values. For instance, here I'll set this to 60, that's middle C, and 64, which is the E above middle C. And I'm using the phaser tilde object, which makes a sawtooth wave. And that's useful here because the overtones are sometimes the ones that are the most detuned and produce the interesting effects. So just give a listen to that again. Okay, so the major third, 4 half steps, is a 5-to-4 ratio, mathematically speaking. Or that is the closest ratio. So if I were to type in 60 here, 261.6, and now if I type in a ratio of 5-to-4, you can see that this major third, the perfect ratio of major third, is 261.6 to 327.0 something. It's very, very close. And you can see over here, when we translate those values, 60 stays the same, but a 12-tone tuned third is actually a little bit sharp, so 2.5 cents sharp. So try to hear the difference between those two. Here was the slightly out of tune version, and then here is the perfectly in tune version. So you can hear that this one is more static. It sounds almost like a rock or something. And then this one has this wavering quality. And you might want that wavering quality. So using these kind of tunings are really good for you. And then over here, these, you might want that rock solid, perfectly in tune quality as well. It's even more obvious when you use the full triad. So this would be a C major chord, 60, 64, 67. So I'll set this to 60, and then I'll set this to 5-to-4, and then the perfect fifth, which is close to 67, is 3 halves. So you can see this is 391.9, this is 392.4. And so now I'm using oscillators instead of the phaser, so we'll get just a pure sine wave for each pitch. And then this is the perfectly in tune. triad. Again. So again, this has this maybe pleasant wavering quality to it based on the out-of-tuneness of those intervals, this slight out-of-tuneness from the perfect ratio. And then this version is also rock solid. The pitches almost seem to blend together. So when you use these conversion factors and understand the math between the relationships in tonal harmony, you can start to do very specific things with those values for your own music. Okay.